and welcome to the NRMN Health Research Talk. I'm Ann Smith. I'm here today with Dr. Sejong Bae. Dr. Bae is a professor of medicine with the UAB Division of Preventive Medicine and co-director of the Biostatistics Shared Facility at UAB Comprehensive Cancer Center. He'll be talking with us today about why do researchers need biostatistics. Dr. Bae, welcome.
Thank you. Thanks for inviting me to this session, and I'll be talking to you about the importance of biostatistics in various aspects of scientific research today.
Very good. Thank you. And it is an important topic that we need to know more about, and why it's important to involve the biostatisticians early on and throughout the process.
Especially in these days with the funding environment, interdisciplinary research is very important. Collaborative team science is really important, and biostatistician plays a crucial role in the collaborative science in this competitive funding environment.
Very true. So what will we learn today?
So we'll basically talk about the role of biostatistics in biomedical research, in clinical research, and especially in the research grant and funding environment, and then role of communication between the team members in the interdisciplinary team, and the steps of using statistics in research grants. The sub-items include identifying your research question and type of the study that you plan to conduct, and decide on the appropriate endpoints or outcomes, and conducting proper power and sample size calculation for the study, and appropriate statistical analysis plan following the sample size and power calculation. All these are crucial elements when you conduct a study, and especially when you apply for a grant proposal. These are the key issues that you need to touch and base. And also, the reason why you need to talk to biostatistician early enough in the grant proposal is the communication. The biochemical scientists may speak the English with the biochemistry jargon in it, whereas the statistician can speak the English with the statistical jargon in it. So those two English are different.
Yes.
They need to come to a layman's language to be able to communicate and go and achieve the goals of the grant and research proposal. And also, a lot of cases, a lot of junior investigators, even sometimes senior investigators, trying to achieve too much. So that's where the study design comes into play, and statistician with the experience can help guide the investigator to be able to achieve the reasonable goals during the duration of the time.
Very good. Yes. Well, we'll look forward to finding out more about that. So why is biostatistics important?
These days, everywhere you go, look at the biomedical research or clinical research, everybody talks about the big data. So how do you prove those treatment worked or big data, whatever it's proving? It's all evidence-based or data-driven. So wherever you see the data-driven, evidence-based, that's where the biostatistics comes into play.
Yeah, so it's all the way throughout.
Beginning to the end, and then sometimes bed to bench side and bench side to the bed. All these are required, to provide the evidence to show the treatment works or intervention works. Biostatistics are needed to prove it.
So how can biostatistics help in predicting disease?
Predicting disease, so we're going to talk about some of the celebrity, the event that went on last year, a year ago. So first thing we're going to talk about is the genetics and disease and medical drug studies, some of the things. So in 2015, August, the former President Carter came out and he said, I have a terminal disease, and he was diagnosed with the melanoma, which is type of skin cancer, but it has spread to his brain and liver. So when he came out forward, but he did not know where to go, but he got admitted to the Emory Hospital Cancer Center in Atlanta. So the doctors advised to him to go through the regular routine, usual care, which is including surgery plus radiation, and this drug called the Keytruda, which is the immune therapy drug. What immune therapy drug is helping the patient immune system to fight the cancer. how did they know the Keytruda drug worked? It was all based on the evidence. You can see the overall survival of the patient. Merck came up with this drug, and they did go through the pivotal study, big study, and based on the biostatistical evidence, they were able to tell the Keytruda is working better than the competitive drug. And also what you need to know is that that drug does not work for all the cancers. Initially, the drug was approved for the small lung cancer as well as the skin cancer. Those were the only two disease types. So to show whether that drug can work on the other disease, other types of cancer, they also need to do another trial.
Yes.
So all based on the evidence of the data that they can show whether the drug is working in the different disease or different type, of the disease.
What is this graph showing?
The overall survival, that's the overall survival graph, which was the key outcome for this drug. So basically the top graph with the green light is the 3 times a week, and the top uppermost one is the 2 times a week. So basically 2 times a week, 3 times a week shows a similar overall survival benefit versus the other drug, that's the competing drug, shows the lower survival rate. Here's another example with the prediction of the disease based on the markers that they have identified. Angelina Jolie, the actress, and announced that he's going to go through the mastectomy based on the gene mutation that they have found. So she found out that during the regular routine checkup with her doctors that she had a BRCA1 gene mutation. And based on the lot of data, evidence, that's where the statistics comes in. So they find out predicting the cancer. If you have a BRCA1 mutation, you have 87% of developing cancer during their lifetime, and 50% of developing the ovarian cancer in a lifetime. So all this prediction was based on the statistical work that went in. And also her genealogy, family history of cancer. Her mom was diagnosed with the breast cancer and died of the ovarian cancer, and her grandma died of the ovarian cancer as well. So based on the family history and this gene mutation, she decided to go through the mastectomy first, and then after the recovery, she did the oophorectomy, which is to avoid the ovarian cancer. So all these, how do they make these decisions? It's all based on the data that went in the background to make sure it's predictable.
So the data is very important in order to make those decisions.
Yes, especially in the grant environment, you need to have preliminary data and to show, and you need to show the grant reviewers how you're going to prove all these claims that you want to achieve.
So tell us about what biostatistics is.
So we basically talked about it, but the biostatistics is the art and science of summarizing data and quantifying evidence, which is evidence-based, data-driven in the field of biomedical and clinical researches. And scientific and clinical researcher often collects a lot of data to answer research hypotheses, such as did the new intervention work? How did the oncologist new Keytruda work? It's all based on the data. You saw the survival graph earlier slide. So based on the statistics, statistician helps to come up with a sample size for the study based on the primary outcome that was identified, which happened to be the overall survival in those cases. That's how they show the drug is working properly and providing the benefit for the overall survivor. And also sometimes are the group being compared different or equivalent, depends on the study design and study type. So Keytruda may be there for a while, I mean maybe a blockbuster for a while, but they have to release the patent after 10 years, patent expires. So competitors can come in and develop the similar material. But to show that similar material is equivalent, you need to show as similar efficacy as possible for the competing drug. So that's where the statistics comes into play too, to show based on the data, evidence-based, it's working or it's as equivalent as possible. The good thing with the equivalent drug is they may come up with a drug that's a lot cheaper. Yeah. Right now, the Keytruda costs $125,000 per month for a cancer patient. So if they can come up with the comparable drug at the lower price, it's better for the cancer patient.
Yes.
Yeah. And then also statistics comes into play. Is the new method sensitive than the old method to compare it? In old days, when you check the thermometer or temperature of a person, what was the temperature gauge, the instrument that we used?
Mercury and 98 degrees?
Yeah, mercury at 98 degrees. And nowadays, if you go to a doctor's office, how do they do it?
Digital?
Digital, they just swap it, your forehead, right?
Oh, I haven't had that done.
Oh, you haven't had that done? I had that experience. So basically, you have to show that the new one is as sensitive as the old one. Mm-hmm. Yeah. Those are some of the usage of the biostatistics.
Yes, and then we talked about the risk.
Yeah, and Angelina Jolie case, having that mutation of the BRCA1 gene and chance of developing the cancer. Yeah. Yes.
And Dr. Bae, how do biostatisticians help?
So we talked about the medical examples that hit the news, recently. And biostatistician can help not only the grant proposal that young investigator, senior investigator putting it on, but clinical trials, as well as a lot of different medical researches. We also help on the manuscript development and abstract, and sometimes investigators come up with the approach that may not be appropriate. And biostatistician can help properly analyze the data. And especially with the NIH Rigor and reproducibility becomes really important. Designing the proper study, organizing the data, which is part of the reproducibility, and proper analysis and interpreting results, and drawing valid conclusion from the study and presenting the data properly is really crucial, important. Those are the key components that they see in the rigor and reproducibility. And also when you write a grant proposal, if you're collaborating with a statistician, it adds a big credibility to your grant proposal. In like pharmaceutical company setting, biostatistician is a must in a collaborative team with a PI and biostatistician, data manager, and clinical research associate. So in summary, biostatistician should be a part of the study from the very beginning, when you're concept stage and developing the proposal, and then submitting the proposal, and when the study begins from the very beginning throughout the study till the end.
And part of the end of the study is the manuscript development to publish the results, to send that to journals to be read by other investigators who are studying or interested in similar things, and you need the statistical analysis described accurately.
It is the case. It may be the beginning of the new study based on your finding. You may be able to apply for the future study based on this, the data that you generate from the study.
Who needs statistics or biostatistics?
So statistics is for every researcher who's doing the research from the bedside to the bench. Sometimes it goes back. Sometimes you find great findings in the lab, but you want to translate it into the bench side, right? A bench to bedside, then the statisticians can also come in and help out, whether it's a really promising the evidence or good evidence and so on. And sometimes it goes to the backward from bedside to the bench side. Sometimes clinicians find something interesting phenomenon while they're doing the treatment, and then we can translate back they translate back to the bench side, and we can also help design a proper study for those occasions. So statistics and biostatistics in summary is unique among academic discipline that statistical authorities needed at every stage of virtually all researchers, including planning the study when you do the grant application and selecting the sample. A lot of cases, all the statistics are based on the random phenomena. So if you do a batch mode of the selecting the sample, that may bias the results, and that may create a problem reproducing the results. And then managing the data is very important, and also interpreting the results properly is really crucial.
So here is our next segment, the first clinical trial. The population were sailors who got scurvy in the 18th century during long voyages. I think many of us have heard stories of sailors who got scurvy. So this was when they first tried to figure out what caused it. So the sample were 12 sailors with scurvy on a British ship, and they were treated by Dr. James Lind.
So James Lind initiated his first clinical trial documented in the history. If you look at the study protocol that he provided, if you compare that with today's study clinical trial protocol, there's a lot of, rigor ranking. So here's the first clinical trial protocol, right, that's been identified. He gave 2 patients with a cider, and 2 patients with some medication, 2 patients with the vinegar, 2 patients with the seawater, and 2 patients with the citrus, and 2 patients with the spicy paste and barley and water. And he find out that the one who got the citrus improved. So if the effect was so great, others did not improved. The Dr. Lind inferred correctly somehow the citrus was the cure for the scurvy, but it took another 100 years to really prove, based on the data, that the citrus is the real cure for the scurvy. So in this protocol, he did not talk about what kind of statistics or method was used. If it was a modern clinical trial, you're going to hear a lot of regulatory issues. Some of the things that he was not mentioned is like randomization, right? It's a crucial randomization, and blinding is a technique that is used to address the biases. Sometimes it depends on the symptom, the doctor may provide a different treatment options. So randomization is very important, and blinding is another thing. To investigator, I should not know what kind of treatment the patient or the subject is in, so to avoid any kind of bias that can be human bias that can be created. And then the things did not mention in this protocol is informed consent. These days you have to have informed consent to be in the clinical trials, and statistical method to be used, or how he defined the significance level or p-value of the conclusion that he had made, and power and sample size things were not discussed in the first clinical trials.
Great, and we'll go into a little more detail on all these different components of the research, including we have one on informed consent by Dr. Shodake at Tuskegee University. That's very good.
So NIH came up with these guidelines on the rigor and reproducibility. There's a link contained in this slide that the audience can go and look at it. Basically, if we put it in the simple term, rigor is a rigorous design, method, analysis, and interpretation and reporting. And reproducibility is basically validation. When somebody comes back and do the study again, can you reproduce it? That's the validation. So you have to have a good protocol of doing the data quality control management, and so that way somebody else do the same experiment should be able to reproduce it.
Yeah, so when other researchers read about it in a journal, they can do the same experiment and hopefully get the same results,
right,
reproduce the same results.
Right, NIH is really big on the rigor and reproducibility now.
Great, great, and that's now components of the grant applications that they have to say how they're addressing that.
Rigor, yeah, is really important, yeah. And reproducibility is when you write a paper, you got to be able to show that's valid. So another way of looking at the role of statistics is if it is a deterministic event, you don't need the statistics. Deterministic event is like you have a bank account, you know how much is there, and you write a check, you know how much is going to go down. But the random event is where the statistics is needed. What it means by random event is like when we toss a coin, right? What is the probability of seeing the head?
50-50?
50-50, right? So if all the audience in this video segment throw a coin, do you think we'll see a 50%?
Perhaps.
Perhaps, right? So that's a random phenomenon. Let's pretend we have 10 of us and each of us throw a coin. The chances of seeing the head is 50%, but that's a long-term random event. Sometimes we may see 0 head, sometimes we may see 5 has, 1 has, and 2 has. So that's a law of large number. When we do the experiment long enough, based on the random phenomenon, it's going to approach the 0.5 or 50% chance. So that's where the statistics comes in and help out with the bring the evidence base.
So what are some steps in using statistics in research?
So you need to communicate with a statistician early enough. It's never enough to emphasize the communication among the team members, among the team members. It's really crucial. We talked about the English with the biochemistry component jargon in it, English with the biostatistics jargon in it, then they need to come down to layman's term to be able to communicate and to accomplish the goals. During the communication, we need to identify the questions and identify the type of the study and decide on the appropriate endpoints based on the dollar figure and time frame and resource that's available for the study, and appropriate analysis plan and sample size and proper data management and analysis plan. So here's a web link that you can go and look at it. I mean, this video, cute little video, talks about the communication, importance of the communication. In this video, the biostatistician and lab researchers are having a communication where lab researcher uses a lot of lab jargons versus biostatistician uses the biostatistics jargon. And lab researcher comes to the biostatistician on Friday afternoon. Usually that's not the best time to approach the Friday afternoon before the grant is due.
On Monday.
On Monday. Right.
Yes, I looked at the cartoon. It is cute. And the researcher wants to use 3 participants in the study and wants the biostatistician to confirm that that's the amount that he needs.
Yeah,
So,
but biostatisticians keep asking question about what do you really want to show? And that's where a lot of variability and rigor comes in to play, not just based on the, like, mom cooked it this way, my mentor used the 3, that's why I'm using 3 is a bad choice.
Yeah, so we encourage you to look at that video and think about it.
Yeah.
So tell us more, what is the rigor and reproducibility? We've talked about that, but what are some of the details of it?
So, I mean, are you having a proper study design and looking at the proper outcomes and statistics that's involved? And for the reproducibility portion, you need to have a good data quality management plan in place. And during the grant review process, I mean, what are the components the grant reviewers looks at it? Those are some of the items we're going to visit and look at it.
So what is the first step?
So you have a scientific idea of what you want to do, scientific objectives, but that needs to translate into a statistical hypothesis which can be testable. Otherwise, unless you have data-driven or evidence-driven the results, you will not be able to show whether your treatment or intervention worked or not. So first step, the hypothesis, the definition is an assertion subject to verification of proof as a proposition stated as a basis for argument or reasoning. So it needs to be specific, null hypothesis versus researcher's hypothesis. Sometimes it's called the alternative hypothesis.
What is the null hypothesis?
Null hypothesis is just the complement of the alternative hypothesis. So if you want to show the drug is working based on the certain criteria, like, your survival is better by how many months, then alternative null hypothesis will be it's not as better than the other one.
Great, so it's the opposite of it.
Opposite of it, basically. Yeah. So here's a question: does the new treatment improve the survival of breast cancer patient? This is a scientific question that you want to prove, right? We want to prove that new treatment is better, improve the survival of breast cancer patient, but this is really broad.
Yes, very broad and general.
Right.
We don't know how.
Right. So bad hypothesis is just putting in together new treatment improves the survival of breast cancer patient. And a little bit better hypothesis is by adding a month, by how many months. It needs to be quantifiable. That way we can do the proper testing. But the new treatment may not be effective for the all breast cancer. There are a lot of subtypes like BRCA mutation ones or triple negative cancer. So it needs to be really specific to that subgroup population where the real treatment effective will be in. So all those things need to be clearly written up in the hypothesis. And also we have to identify the type of the study that you're conducting. It all depends on the resource, time, constraint, and budget issues. Let's say you have a 2-year, usually R21 grant is for 2 years. But if you want to conduct a study for 3 years survival, then that's not feasible study, right? So based on the circumstances, the resource, money, and time constraint that you have, you need to come up with the best idea, best feasible study design as possible. These are some of the study design that's feasible, like retrospective, observational, case control, cross-sectional, prospective, and randomized trials. So it depends on the nature of the study. Statistician can talk to the investigator and provide the best study design that's possible. And if you don't mind reading the case study.
Okay. Case study 1, observational. An investigator attempted to study whether users of brand A or brand B spermicide had a lower probability of developing tubal infections due to chlamydia. The investigator identified 100 women using each brand of spermicide, followed the women, and did cervical cultures for chlamydia on a yearly basis for 5 years. The investigator found that women using brand A spermicide had 1.5 times as many positive cultures for chlamydia and concluded that brand B spermicide is associated with lower rates of tubal infections.
So the things about this observational study is you don't do any intervention. So like basically they identify the subjects who is using this brand A and B and then follow them and see what happened, right? But how do you know?
There could be confounding factors.
Right, confounding factors. Brand A, somebody may prefer brand A versus brand B. It depends on it could be a price issue, it could be the shape, or it could be the advertisement issues, right? So this creates a bias. So given the circumstances, money and time constraint, this may be a best design, but it does contain a lot of factors that create a biases. So next example, if you can read this case study.
Okay, this one is the prospective design. An investigator attempted to study whether users of brand A or brand B spermicide had a lower probability of developing tubal infections due to chlamydia. The investigator randomly assigned 100 women to each brand of spermicide, followed the women, and did cervical cultures for chlamydia on a yearly basis for 5 years. The investigator found that women using brand A spermicide had 1.5 times as many positive cultures for chlamydia and concluded that brand B spermicide is associated with lower rates of tubal infections.
So in this study design, you got a longer study period and then the randomization is, so that reduces the bias that can be created in the study design. So it depends on the nature of the study and resource constraint. You can come up with a study design that fits the study purpose.
And it seems they came up with the same results.
It came up with the same results, but this one is reducing the bias, so the conclusion is more conclusive than the other one, yeah.
Good.
Right.
So there's a greater probability that it could be right.
Not greater probability. You've been controlling the experiment, the clinical trial, so you know it it reduces the bias. If some region brand A is preferred over the brand B, for those patients, you don't know why they choose those brand versus A versus the other one. But here it's all randomized, so you're reducing those bias effect, and you see the conclusion.
So it's a stronger design to include randomization.
Right, stronger to avoid the biases. And this can be generalized in the other place, not based on the preference of the brand, but it's all randomized.
So how do you decide on the appropriate endpoint or outcome?
So we talked about earlier, right? If the study duration is 2 years, and if you are interested in looking at the 3-year survivor, that may not be feasible. So based on the communication between the investigator and statistician, maybe you need to come up with a surrogate marker, which is a kind of indication for the long-term outcome, which can be achieved during the duration of the study. 3-year survival in 2-year grant is not, you can't do it. So surrogate marker could be progression of disease at 1.5 year or 1 year, or different kind of outcome, or tumor size, or based on the imaging, whether tumor is progressing or not progressing. All these different things can be studied and discussed together to come up with the proper endpoint.
And you have to do that ahead of time to decide what it can be.
Yes, and based on the endpoint, the power and sample size calculation can be carried out. Depends on the endpoint. Sometimes the power and sample size dramatically varies, so it's really crucial to talk to the investigator, statistician early enough. So you gotta really think through whether that outcome measurement is really answering the question that you want to address. You may not be able to capture the 3-year survivor, but the surrogate marker, which is progression-free state, is the surrogate marker for the long-term survival. Then it kind of answers the question. If it reduces the tumor size, right, you know it's going into the right direction. So those are the things that you need to be talking, and the surrogate marker or the measurement needs to be accurate and should be complete. You need to make sure you have all the data, and then not be influenced by the process of the observation. Study design needs to be really solid to be able to achieve all these goals. So as we talked about earlier, right, statistics is the key. It's all based on the random phenomena, whether they develop or, the progression is up or down, all those are random phenomena, and assignment of the group is random phenomena. Statistics is there to infer back to the whole population, whole disease group. Even though you study with a small number of groups, small number of subjects, based on the statistics, we can provide the evidence that brings back to the whole population. Kikuruda study that we looked at it earlier with the former president Jimmy Carter was based on a certain number of people, but that N is like maybe thousands of subject patients who went through the clinical trial. But based on the statistics, we can infer back to everybody, the population who has the same types of disease. That's where the statistics comes in to help to conclude, to provide evidence.
So what are some questions about inference?
So it's all based on the budget and the time and research criteria. How do we calculate the estimate from the sample? And how can we say about the accuracy of the estimate? And how can you make inference about the population from a sample? And how confident are we about the correctness of these inferences? All these are based on the statistics. They're based on the endpoints and outcome, different statistics and different approaches are available.
So the confidence is something that we'll talk more about too, than on the confidence interval.
Right.
Is how confident you are that it's accurate and that it can apply to other populations or greater populations.
Right. So can you read this simple example that has been conducted here in UAB?
Yes, so this example is a population of patients with glioma, which is a very bad form of brain cancer. They are given an experimental treatment. The parameter is the proportion alive after 1 year after treatment with this experimental agent. And the sample is a set of 10 such patients.
So the parameter that we are interested in is the proportion of patients who's arrived at the 1 year of the treatment. So we can estimate the parameter just dividing 7/10, which is 70%. That's the estimate for this sample, but we can infer back to the population using the statistics. So using the statistical formula, we can come up with this 95% confidence interval, which is the confidence that we have with this estimate of coming up with a 0.7. Confidence interval ranges from 0.3475 to 0.9333. What it means is if we do this experiment, 10 subjects in different occasions, many times, the lowest percentage that we're going to get, patient alive at 1 year is 34%, 34.75, or it can go up as high as 93.33%. So that interval is wide, means estimate is there's still a lot of variability. The reason why we get this large variability is a small sample size. Sample size is equal to 10, so that's where the variability comes in. So if you want to reduce the confidence interval, we can increase the sample size. If we happen to see the 70% of the patient alive at 1 year with 100 patients, then the confidence interval narrows down really dramatically. So now if we see the 70 of the 100 patients alive at the end of the 1 year, then the confidence interval goes from 0.60 to 0.78.
So when you increase the number of patients in the sample,
Right.
you get greater confidence, a degree of confidence, and that
Smaller, you
yeah,
get more precision on the estimate.
yes, and it's closer to that 70% or the 0.7.
Right. Which provides you more confidence about the success of this treatment.
Yeah, because the 0.6 to 0.78 is a lot smaller than the 0.34 up to the 0.98.
Right, about 2 to 3 times smaller, narrower than the,
Yeah. Suppose we know from historical data that 50% of the patients with these tumors treated conventionally survive for 1 year, so that's 50%. So can we infer that the treatment with 7 out of 10 alive after 1 year is effective?
So what do you think? I mean, guesstimate? How do you feel?
Well, that confidence interval with the 100 patients looked good. So maybe this new treatment is better.
But with the 10, I mean, we have a subject of 10. So if we had the 100,
right. So I think it's a too small of a sample size.
Right. So I mean, if you were FDA sitting on the committee, do you think you'll approve this drug to move forward to treat the patient with the glioma?
I don't think I would.
Yeah. And if you were a director of the company who's trying to develop this drug, do you think you're going to go ahead and give a go sign?
I think we need more research on it, more studies with a greater sample size.
Right, true.
Get a better confidence interval.
Right. So the sample size, smaller sample size, the experiment or clinical trial is using the very early stage to see whether we have some evidence towards whether we can go forward or not. So for this occasion, right, our intuition says that 7 out of 10 is not sufficient to conclude the proportion surviving 1 year in the population is greater than 50% based on the confidence interval that used those. So all those confidence interval is calculated based on the biostatistical methods that's behind. But why does our intuition say that?
Because 7 is greater than 5?
7 is greater than 5, but when we look at the confidence interval, you kind of look at it, may not be, right?
Yes.
So in logical basis, it is not unlikely that something that happens 50% of the time in the long run will happen 7 or more times out of 10. And think about the towing crossing example that we discussed. And using the statistics, I mean, these are the actual statistical p-values that we calculated. So if we see the 7 out of 10, right, I mean, the difference that we can claim is the p-value significance of 0.17188. So usually in the statistics, we use the p-value of less than 0.05 to conclude whether it's different or not. So based on p-value of 0.17188, we can conclude it's not statistically significant. But if we saw 9 out of 10 are alive, then we can say, yeah, I mean, p-value is 0.0107, for which is less than 0.05. Then we can claim, yes, it's working and it's better than the 0.5.
Mm-hmm. Yes, and the p-value is the probability.
Right.
And so then that column there has the probability.
So we basically went over is the convincing evidence that the treatment worked based on the binomial probability. It's not the case. That's all based on binomial distribution and probability. And was 10 patients enough? Was this good experimental design? So all those needs to be thought out. This could serve as a good preliminary study for the future trials and see how many subjects that we may need for the future trial.
So if we had reverse circumstances that out of those 10 patients, only 3 were alive.
Probably, I mean, you probably don't want to push forward the 7 out of 10. Based on those preliminary experiments, you may do a power and sample size calculation for the future trial. And we're going to talk about the power and sample size, what it means by power and sample size in the grant application or study design.
So what is power?
So there are two types of error, and that you get to see a lot in the grant application or the clinical trial studies. Type 1 error is one that is the probability of rejecting null when null is true. And it's also called the level of significance, or alpha. And there is also type 2 error, which is the probability of failing to reject null hypothesis when null is false, which is also called the beta. And then here comes the power. That's also another probability rejecting null hypothesis when null is false, which is also sometimes used as 1 minus beta. But using the layman's term or the judicial example, this is how we can define the power and type 1 error and type 2 error.
Power and error using the criminal justice system, the null hypothesis is the defendant is innocent. The alternate hypothesis is the defendant is guilty. So the type 1 error is the probability of finding the defendant guilty when the defendant is really innocent. So that's what alpha is. So finding him guilty when he's really innocent. Type 2 error, or beta, is the probability of finding the defendant not guilty when they are indeed guilty. So the 1 and 2 are when you find that it's the opposite of what it really is. And then the power is the probability of finding a person guilty when they are guilty. So when you can find the true outcome is the true outcome.
So that's why the power is really important when you design a study.
What are some important things to consider when determining the sample size?
So it's really crucial. I mean, sample size, it's all based on the resource issue and the constraints that you have in the study. What is the desirable effect size, detectable differences? Sometimes clinical difference versus the statistical difference comes into play. I mean, if you have a large enough sample size, you'll be able to find the very small p-values. But if it is not clinically meaningful, then there's no value to it. Mm-hmm. So it's given the study design and resources that you have it available, it's really crucial to identify the proper design effect size. And depends on the outcome, those effect size may vary. Like it could be a continuous outcome, it could be a dichotomous, a proportional, or it could be a survival outcome. And then you need to know about the previous information about the variability of those outcomes. It usually comes from the literature or the research that you're doing in your lab. And do you have a limitation on the sample size? We'll look at some of the examples later about the sample size issue, but the investigator needs to have a buy-in onto the sample size. And like in the human trial, not everybody stays throughout the study, so you also have to think about the dropout attrition rate in the sample size calculation. And another different consideration that you have to think about in these days with the CBPR, community-based participatory research, we use a lot of group randomized trial, then you have to think about the intra-class correlation to account for the proper sample size calculation. So here are the real-life example that I had to face one time. This is a preparable design, but the investigator had a resource issue. The investigator could only fund 50 patients to the study. So, but I did both way of scenarios. I mean, the investigator was interested in comparing the treatment 1 versus 2, but given the circumstances with the 50 subjects, he could only compare the within treatment with the historical, and then do some the exploratory study. But he also wanted to do the comparison across the groups. That's what the scenario 1 is. I basically provided, if you want to compare the across the group, it may cost you a little bit more, 78 subjects, versus if you follow what your constraint, you may need a 48 subject. But here are two different scenarios. But the investigator also were interested in looking at the different outcomes. So he was able to convince the sponsor to go with a preparable scenario. So it depends on the resources and constraint that you have. A statistician can help you design the study, but preferably you can go with the ideal study design that you want to pursue.
But it depends upon then the resources or the funding available and the time and
Right.
other.
So different types of study design can be developed for the investigator.
Another good reason to plan ahead. And
Plan
start
ahead
early.
and talk to the statistician, and by communication you can identify overcome the barriers that you may have, and he was able to convince the sponsor to add more and to raise more money to get more patients in.
So tell us about some key components in a power section.
So in the power and sample size calculation in the grant proposal, you need to provide the description of assumptions. What are the differences or effect size that you're going to detect and variability that you have, and it must be really clear and reproducible. Sometimes biostatistician in a grant review panel actually do the calculation, see whether they can come up with. So you need to make sure. And then if you have a dropout in a clinical trial, you need to provide the evidence of, based on what you're assuming this much of the dropout rate. And you can dig it up from your literature or based on the history of your study. And then, if possible, hypothesis-specific calculation should be provided.
And all of that should be included in the
grant writer, basically, and based on the sample size calculation, there are numerous. A lot of different analysis approach that's available, but a lot of mistakes the junior investigator, sometimes even the senior investigator makes is the sample size calculation should be in concordance with the analysis plan that you have, but sometimes in the grant review panel, I get to see. Yeah, sample size calculation using A approach and data analysis using B approach. If there is discordance, then that's a big hit you're going to face.
Yeah, that's a problem.
Yeah.
So another key point to think about for the researchers is what the type of analysis that will be conducted, and plan that out with the biostatistician.
Right, it's very important.
The hypothesis is the mean systolic blood pressure will be lower at 1 year in patients randomized to the intervention arm than patients randomized to the control arm.
So this could be a hypothesis, scientific hypothesis one may drive, but when you go into it, what is the outcome that you're looking at? Are we looking at the mean systolic blood pressure? How much of the drop, right? So unit do we want to see? Those are the things that we have to consider. What are the comparison groups, right? Are we looking at what kind of comparison? Are you looking at the placebo drug or a competing drug? Depends on. If it is a competing effective drug, then it'll be really challenging, not easy to show the differences unless this new drug is really effective. So all these different things need to be thought out. And then do you have a preliminary data? Based on the preliminary data, you will be better calculate the power and sample size. And some of the, as we talked about it before, limitation on the consideration like money issue, resource issue, and then type of test for power that needs to be developed based on the outcome. And what type of difference, how much of the difference do you expect to see? A 10 unit difference drop or 20 units? And how much of the dropout? Like, do you expect to see 20% or 10% of the patient dropping out?
So you need to plan ahead for specific measurable differences.
All those things needs to be planned out ahead, yes. If it is a clinical trials, you have to have a protocol written up. And if you change anything, you have to amend the protocol.
What does the clustering mean under the special considerations for the
clustering
sample?
is like CBPR, community-based participatory research. You may have to random assign the whole cluster, whole town into one treatment group. That's where the clustering comes in.
I see.
Yeah, and then that's where the special, the adjustment called the interclass correlation, ICC, needs to come in for the power and sample size calculations.
So now we're moving on to reproducibility.
So reproducibility, it's all about the data management and quality control of the data that you have throughout the study. And when should you involve the statistician? From the beginning, when you develop the database design, I worked in a pharmaceutical company for a little bit, and based on my experience, the interdisciplinary team consists of the PI, who is the clinician, and then statistician is there, and there's a clinical research associate and data manager. Minimum 4 become a team for the study, and they do communicate thoroughly throughout the study from the beginning when they initiate the study and then create a data collection form, database design, and during the study and throughout the study, they have endless communication going to deal with all these data management issues and other things that pop up.
So considering issues with outliers, the range check, logic check, double data entry, so plan ahead for all of those possibilities.
Plan ahead, but it also depends on the budget. I mean, if it was an NIH study, you got to think about best possible scenarios to deal with the data issues. Yeah, sometimes it may not be feasible to do the double data entry, then you can do a random selection of certain percentage. But the outlier checking, range check, logic check needs to be really built in well. Then you save a lot of time in data cleaning later part of the study. So in the data management quality control, I mean, when I do the lecturing, I use this GIGO. GIGO, but what it means is a garbage in, garbage out.
Yes.
Basically, unless you do a real good quality control on the database that you develop, I mean, putting the data into electronic format does not mean data quality is good. You have to really stay active and throughout the process to make sure the data is in good shape.
Ensure that quality. Garbage in, garbage out is not good.
Right, not good at all, not good at all. If you don't mind, can you read
So data management, the act or practice of directing, supervising, or controlling the use of information organized for analysis.
So that basically sums up, but this also requires a lot of communication among team members, including the PI, who needs to make the decision based on the resource available. Yeah.
Great. So it may involve selection of participants, developing recruitment reports, documentation of data sources, developing data collection tools, chart abstraction, documenting data integrity, and coordinating data warehousing. All of those very important pieces of the data management plan.
And you can also read this.
May also involve data manipulation, data security, we know how important that is, and submission of data and documentation at completion of study.
So when I work with a lot of investigators, sometimes I get like Excel spreadsheet flying through on Friday afternoon, and when you look at it, right, this is the one example from the investigator that I worked with, and if you look at it, the data is all over the place. I mean, it could have been better to come up with a mutually exclusive, not open-ended question. I mean, it's really important to control the data in the beginning, not at the end when you analyze the data. That becomes a really big headache, and if you did not specifically define the data, then that becomes a real nightmare for the data management, and especially when it gets to if that variable is important to analyze the data.
Yeah, so if you get a spreadsheet like that, how do you make a report from that?
It takes a lot of time going back and forth with the investigator to make sure what the investigator really wants to achieve, and sometimes it may not be feasible. Data is already collected, and there's nothing much you can do. Yeah.
So plan it out before you start.
Right. So you can read this slide for the audience.
Okay. So the key components in data management and quality control plans. A clear explanation of how data will be handled, entered, archived, etc., and plan it out, explain it at the beginning. Some explanation of the data management capabilities, so what your staff and your office and laboratory
Some
can
of
do.
those components are very important if you conduct a large trial in the grant application too.
Yes. So an explanations about how data will be cleaned. What does that mean, how it will be cleaned?
So, data coming into electronic format does not mean it's a clean data. You got to do a outlier check and logic checks, and if there are discrepancies, you need to go back to the investigator resource to get it corrected. So that's where the data cleaning comes in.
And it's part of the quality control.
Right, yeah.
So then it goes on with any considerations regarding quality, for example, the range checks, double entry of data, certification of staff. And then lastly on this list, data security. Who will handle data and how will it be secured? And that's even more and more important these days with all the different electronic storage of data and
HIPAA regulation and FISMA regulation that's coming into place. Data security is a really key issue that whole team needs to really think through. And this is another example of the data analysis. A lot of investigators get to figure out how to click, and do the black box approach of the data analysis. And this one investigator came. I'm looking at this data, and I thought disease-free survival rate should always be less than equal to overall survival. Somehow in my data, when I run the black box approach, click, and get this results, it's opposite. It does not make sense, right? I mean, your disease-free survival is greater than the overall survival.
Overall?
Yeah, the patient passed away, but disease-free survival state is still going on. And that's where the statistician comes in and play. If you do a black box approach and run it, right? I mean, this is something that you may face, but when I talk with him, yes, he did not check some of the assumptions. He did not check the data quality. When I looked at the data, he had a lot of missing data, which is censoring. It's called the censoring in the survival analysis, but there are limitations of how much data can be censored. And most of his data was censored. That's why these kind of things happen. And I had to explain about because of your data completeness, you may not be able to use this approach too.
So in the 2-year overall survival and the 2-year disease-free survival, what do the MUD and HPLO?
Oh, MUD and HPLO is different subtype of the allotype, but his main interest was looking at the HPLO. And if you look at the overall survival and disease-free survival, it's kind of flipped, and that's where a lot of missing data was. And if you look at the confidence interval, the one in the parentheses, it's really wide too. That's another indication. So you got to look at the actual data, and statistician can help you better to look at the data.
Great, and so you were able to find out where the problems were in the data,
right?
The missing data.
Yeah, and then he agreed. Yeah, later on, I was able to convince.
We've got a summary.
Yeah, home stretch.
Yes. This is what to include in a statistical section in your grant application. The key components of the grant statistical section, the basic descriptive, understanding the nature of your data, so describe what it is, the data, clearly defined outcomes, so that goes back to determining what the endpoints are and the outcomes that you'll be using to measure. The appropriate and state-of-the-art analyses. So you had mentioned using innovative and the newest technology in analytical tools. Any special considerations, multiple testing, for example?
Like if you have multiple outcomes, you have to adjust for the type 1 error rate in the statistical analysis, and that's very crucial.
And write about that, include that in your grant application.
Yeah.
So, and then the hypothesis-specific analyses for each hypothesis, missing values plan. So what is the plan for if there's data missing?
Right, and if you cannot get the data, what are the plans for handling the missing data?
And then attrition analysis plan as well. So when you have people that may drop out, what is the plan for that?
Right.
And then ancillary analyses.
Yeah, that basically summarizes the discussion that we had today. And why include the statistical section? You'll want to have advice from a statistician because your grant will be reviewed by a statistician in the panel. Yes. I do serve on the grant review panel many times throughout the year. So when I read the grant, I can tell whether the investigator really worked with the statistician or not.
You can tell.
Yeah, you can tell. I mean, you can have a bias schedule statistician, but that's different than the actually working with a statistician, and make sure you have that dialogue going on between you and the statisticians. Especially in the approach section, it's really important is the statistical method used sound, and are they using the correct outcomes for the study? Are they using the correct statistical approaches and power calculation is correct and clear rationale for that assumption that you're making? Is it based on the literature or based on the study that they have been conducted? and the statistical analysis that they are using is innovative, and especially in the clinical trial or human trial, they want to see a statistical, the data management environment and the quality control plans too. And as an investigator, they also want to see whether they have been collaborating or just adding the biosketch to the application. And these are the common mistakes that a lot of junior investigators, sometimes the senior investigator. So I'll let you read through.
So power calculations are not reproducible. Power calculations are not based on prior information. Statistical methods proposed are not appropriate. Statistical methods are too general. There may be a lack of detail regarding data management and quality control, or too little effort for statistical investigators. So they may not be giving enough salary funding for the biostatisticians.
Right, especially like a clinical trial, 1% effort of biostatistician. I mean, people know, statisticians know how much of the tiny effort goes into the studies.
Yes, and it takes a lot of time. And it seems from this discussion too that statistics and biostatistics would be a good area for people to go into for their careers, that there's a lot of job security, that biostatisticians are needed in research throughout the process.
That's what I saw in one of the newspaper article. It's a like
an increase in
the job needs,
demand for biostatisticians.
Right.
Yeah.
And then you got to be able to really communicate with the investigators for their needs. That also comes from the experience, but it's a great field. All the drug that people take needs a biostatistician behind to show the evidence based on the data.
Yes.
And a lot of other materials and data mining, data exploration is just going up, and especially with the precision medicine initiative comes out, biostatistics are more needed.
Great, good.
Area.
So what is the summary of our talk today?
So basically we talked about the role of biostatistics in biomedical and clinical research, and the grant funding environment, and importance of the communication among team members, and steps of using statistics in research grants. But it's always, going back to the communication, dialogue between the investigator and the statisticians, and some of the components of the statistical reviews and mistakes that junior investigators, sometimes senior investigators make.
Yes, so in all of that, we hope that viewers will gain a greater appreciation for the importance of the biostatistics throughout the process of research, from the beginning through the end.
Yes, it's very important to involve the statistician from the very beginning throughout and until the end of the study.
And Dr. Bae, thank you so much for talking with us today about it.
Thanks for inviting. Enjoyed it.
Thank you for watching this health research talk. We encourage you to email us with any questions or comments. Also, please take a moment and complete the brief survey on the link on your screen. Let us know what you thought about it and how we can improve it for the future. Lastly, register on the NRMN website to sign up for the online mentoring and be a part of NRMN, the National Research Mentoring Network. Thank you.